All right, so the lesson for today is Vesper. So basically, Vesper is Lewis diagrams in 3 dimensions. All right, so in order to learn Vesper, well, obviously you have to know how to draw Lewis diagrams. You also need to know something about X notation. That is just a way for us to help us draw Vesper. So to begin, I just want to do a little review on Lewis diagram. So here are 4 questions. So please take some time and try to draw the Lewis diagram for these 4 questions. I'll give you like 1 minute for this. All right, so these 4 examples I gave you are all very simple Lewis diagrams. I'm not going to make you draw Vesper diagrams of really complicated atoms. Those are just too big and it takes too long to draw those diagrams. So let's focus on the easier ones. So for the first one, you have methane. You just have a carbon with 4 hydrogens. That's it. You don't have any extra electrons. So I don't think there's a way for you to get this wrong. The second one is water, H2O. If you draw water in a linear fashion, then you will get the question wrong because water is bent. Okay, you can't draw water as a linear molecule, and in this lesson, I'll tell you why. The third one, you have ammonia. You should have something like that. Okay, so you have a T-shaped structure, and the lone pair on top of the nitrogen, it will repel the bonds to the bottom. So you can't draw this with 120 degrees. And finally, carbon dioxide is a linear molecule with 2 double bonds on the carbon, and the carbon doesn't have any lone pairs. So make sure you have all 4 of these correct. These are the rudimentary Lewis diagrams. And we're going to be using these and converting them into Vesper. The problem with Lewis diagrams is that it's drawn on a piece of paper or on a computer screen, so it's flat. But molecules in real life, they're 3-dimensional. And it's very difficult to represent a 3D diagram on a flat piece of paper. So the Lewis diagrams, they don't really accurately model the molecules in real life. Okay, so the angles that exist in the Lewis diagrams are not the actual angles that exist in the real molecule. So for example, if you check out methane CH4, on paper, all the hydrogens are 90 degrees from each other. But real life methane is not like that. So on the right, you have the models of these 3 molecules. And you can see that in the model, methane has a bond angle of 109.5 degrees. It is not 90 degrees. All right, because if you make them 90, you're flat. Okay, you're basically on a piece of paper. There's no way for you to make this 3-dimensional unless you use a Vesper diagram. So to represent the proper bond angles, you have to somehow make it 3-dimensional. All right, and same thing with the ammonia. It is actually not T-shaped. It's T-shaped on a flat piece of paper because that way you maximize the amount of distance between the individual atoms. But in real life, you have 3 dimensions, so it is not 90 degrees. It's bigger than that. Okay, water is bent because, well, we found that the real molecule water is bent due to the 2 lone pairs of those electrons. All right, so how do you draw Vesper? And what is Vesper? So Vesper stands for valence shell electron pair repulsion. Basically, by reading the name, that tells you what Vesper does, okay? You look at the electrons on the valence shell, and they repel each other, so that based on this idea, you can predict the 3D geometry of a molecule in the Lewis structure. And we have 3 rules for Vesper. The first one being that electrons are negative and they will repel each other. Okay, they want to be as far apart as they possibly can be. The second one, electrons are either in a covalent bond or as a lone pair that are not in a bond. But either way, they are electrons and they will repel each other, so it doesn't matter. The third one, they will situate themselves to be as far apart from each other as possible to minimize the forces between them. So knowing this, we can predict the geometry of various atoms. So what do I mean by lone pairs and bonds? Well, by lone pairs, I mean the dots around an atom. They're not part of a bond. So those two lone pairs for oxygen, they're not bonded to anything, but they're still there as electrons. Bonds refers to a covalent bond between two atoms, like the bond that connects the hydrogen to the oxygen. So let's just get the definitions clear. In order to draw a Lewis diagram, you have to understand something called XEE notation. I like to call it AX notation for short. So what does that mean? Well, AXE, those three letters, they all have a meaning. So the letter A is supposed to denote the central atom. All right, and the letter X denotes the bond that A is making. And lastly, E stands for electrons. That denotes the lone pairs that the central atoms have. Okay, so for bonds, for X, if you have a double or triple bond, we count this as one bond. Okay, the reason for that is a double or triple bond will have the same effect as a single bond. They repel. Right, so we just care about the amount of atoms bonded to the central atom, and X denotes the bonds or bond to that atom. To give you an example, I have the four Lewis diagrams I made you draw, CO2, H2O, NH3, and CH4. Here are the diagrams. Now, the AX notation, how do we do that? For the first one, carbon dioxide. The central atom is the carbon, so that's your A. X will be 2 because that carbon is bonded to two other things, two oxygens specifically. And it does not have any lone pair, so you don't have E at all. So this is simply AX2. All right, is that clear? Which means for water, the central atom being oxygen, it has two things attached, two atoms. Okay, two hydrogen atoms attached to the oxygen, so X is 2. Now, we're not finished because oxygen also has two lone pairs, so you have two E's. One E is a lone pair. So this will be AX2E2 for a total of 4 different things attached to that oxygen. And so that's how you would do the AX notation. So can somebody tell me what the AX notation is for ammonia?
AX3E.
Yeah, AX3E. Okay, because the nitrogen has 3 bonds with 3 hydrogens, so X3, 1 lone pair, you write the E. Okay, you do not need to write E1, although if you could just put a 1 there, but no, E is enough. And the last one, methane, is very simple. 1 carbon, 4 hydrogens, no lone pair, so that must be AX4. Okay, do you see how this works? It is important that you know how to write the AX notations from the Lewis diagram.
What if you have a C2H4?
If you have, C2
H4.
Yeah, see, that means you have 2 central atoms. You have to look at them individually. So for one of the carbons, that will be AX3, and the other one will also be AX3. Does that make sense?
Okay, yeah.
Yeah, it's very hard to draw the Vesper structure of something with more than 1 central atom. We'll talk about that a little bit later. So how do you draw a Vesper diagram? Okay, it's really difficult to represent a 3D structure on a 2D paper, so we have to come up with a notation in order to represent 3 dimensions. So here is the Vesper structure for methane. This is called a Fisher projection. Okay, the line that is just a normal solid line, that means that bond is embedded within the same plane as the page. So if you have a computer screen right now, it is probably perpendicular to your desk. That bond is parallel to your computer screen, so also perpendicular to your desk, okay? So you can see that in the diagram, there are two solid normal lines, meaning that the two hydrogens with the solid normal line, they are in the same plane, so they're coplanar with each other. So recall that you learned vectors, they're in the same plane, so you can basically move one on top of the other one, okay? Now, what about the other ones? The dashed line, it means that whatever is attached to it is going into the page. Okay, so now this is not in the same plane as those two solid lines. It is pointing inwards into your computer screen. And the solid triangle means it is coming out of the page. So now you have a three-dimensional representation of your molecule. Okay, so does that make any sense? For something with 4 constituents, like CH4, the way you would draw that is you always draw 2 lines that are in the same plane as the page, so normal lines. One of those lines will come out. Well, I'm talking about the other two now. One of the other line will come out, and the last one will point inwards. So use dash and solid triangles. And the bond angles between all of these hydrogens, they are all 109.5 degrees. Okay, so if you can manage to hold this in your hands, you can see that you can turn it in all kinds of directions. You're going to see the exact same thing. It's perfectly symmetric. Every angle is 109.5. Okay, so that's how you would draw a Vesper structure. And there are many different types of Vesper structures. This is just a small sample of all of them. All right. You need to learn the names as well as how you would draw them. Okay, that's the ultimate goal of this class. And I'm going to just go through the list real quick just to introduce some of these structures. The first one is linear. An example of that would be carbon dioxide, CO2, AX2. That's basically it. It's just in one plane. You don't really need a 3D structure for that. So a normal Lewis structure is good enough. The second one is trigonal planar. That means you have AX3, okay? You form a triangle. So from that diagram, you can see that one of the X is in the same plane as your page, and the other ones, one goes out of the page and one goes into the page. Okay, so that makes a flat triangle perpendicular to the page. So that's how you would draw trigonal planar. Now, I'm a lazy person, because I realized that trigonal planar is in the same plane. You can perfectly represent that on a 2D piece of paper. So instead of me doing this, I always just draw a triangle like a Mercedes-Benz logo. And I mean, that's perfectly fine because it shows the bond angle to be 120. You don't need the third dimension because it's flat. Okay, you can do that or this. Now, the next one will be bent. That would be representative of water. A being in the middle, you have 2 E's and 2 X's. The 2 X's are the bonds. The 2 E's are the lone pairs. Now, why is this bent? Well, because you don't really see electrons. You only see atoms bonded to another atom. So those 2 E's are invisible. So basically, it looks bent. Okay, pretend the E's are not there. That would just be a bent molecule. How would you draw that? Well, same thing as a methane molecule. You will draw 2 lines that are in the same plane as the page. Well, the 2 remaining lines, one comes out, solid triangle, one goes in, dashed line. And it doesn't really matter which ones you choose to be X and which ones you choose to be E, because you can just rotate the molecule and you can get all different kinds of combinations in X and E, so it doesn't matter, you pick your favorite. So the next one beside it is trigonal pyramidal. You would have AX3E. Okay, you have 1 lone pair and 3 bonds. And the convention is to put the lone pair on top. Notice that this is exactly the same as the methane. So a lot of these are really similar. So the good news is you just have to find the pattern and you can know all of them. So trigonal pyramidal, you have 1 lone pair, the E on top. I like to put it on top because it makes a pyramid. It looks pretty clear that way. And you have the 3 X's on the bottom. And the next one, tetrahedral, is just all X's. It's exactly the same as trigonopyramidal, except you don't have an E. The last two are a little bit more complicated. The second last one, trigonobipyramidal, you have 5 things, AX5. The way that you look at this is you have one bond going up, another bond going down. And perpendicular to those 2 bonds, in the middle, you have a triangle. So I don't know if you can see that. Let me draw that triangle out for you. You see that right there? There is a triangle in the middle. All right, and that triangle is perpendicular to those 2 bonds. So it's 3-dimensional. So that means you draw a T with the solid lines, and in the middle, one of those bonds will come out, the other bonds will come in. Okay, and the angle between the 3 X's in the triangle is 120 degrees for all of them. So that will be trigonobipyramidal. And the last one is octahedral. Instead of a triangle in the middle now, you have a square. Like this. So one bond goes up, one bond goes down with a 4-cornered square in the middle, perpendicular to the line. So that takes a little bit of visual and abstract thinking to really see what they look like. But once you get the hang of it, you should be able to recognize the pattern. So
how do we know which one? Sorry.
Yeah, go ahead.
How do we know which one goes forward and which one goes backwards?
What do you mean? Which one goes forward? Which one goes backwards?
Like the dashed line of the.
Oh yeah, that's up to you. You can decide which one you want to go forward, which one you want to go backwards. Okay. You see what I mean? Like I'm not gonna mark it wrong if you switch up the orders of this, because again, you can rotate this to get all the combinations of ins and outs. Now, typically, I like to put the coming out ones on the bottom because, I think that looks more visually appealing. That looks more artistic and realistic. So that's my preference. No, you don't have to do that. Let's actually look at real examples of all of these possibilities. So there are 2 tables on this page. On the top, you have just one line. Notice that the XEE notation is AX. That's it. You have 2 molecules. Sorry, 2 atoms. The steric number is 1. What do I mean by the steric number? Steric number means how many things are attached to the center atom. In this case, only one thing is attached, the X. Okay, so therefore, the shape of this will be linear. And the example would be hydrogen, H2. Now, it's silly to say that one of them is in the middle, but let's say for the sake of argument that you choose one hydrogen to be in the middle. That thing only has one thing attached to it, the other hydrogen. Okay, so the way you draw this is just 2 hydrogens beside each other. It's linear. I believe that one is really easy to understand. It gets more complicated when you add more things on your center atom. So the table on the bottom has the combinations of steric number 2. When you have 2 things attached, you can either have a bond and a lone pair or 2 bonds. Okay, you can't have 2 lone pairs and no bond. That's just an atom. All right, that's not really a molecule. So AXE would be linear. Now, why is it linear? The center atom only has one other atom attached to it and a lone pair, and they will make 180 degree with each other because they want to be as far apart as possible. So by the way, on the picture on the right, the pink represents the center atom, the white represents the X, a bond, the yellow represents the lone pair. Okay, so you can see that that image right there is carbon monoxide. That would be an example of this. Carbon monoxide has carbon triple bond oxygen, and that carbon also has a lone pair, and they stretch out to 180 degrees. And also AX2, instead of having a bond and electron, you have 2 bonds. you are still linear. Okay, so remember, whenever you only have two things, if your steric number is 2, then you must be linear because the farthest distance for that two bonds to be will be 180 degrees from each other, so opposite sides. So carbon dioxide would be an example of AX2. So it's also linear. Do we have any questions regarding this page? Steric number 1 and 2. These two are the easy ones. It gets harder when you increase the steric number. So if you have 3 different things, you can have these combinations. You can have AX3. Everything attached to the center atom, all 3 of them are bonds. An example of this would be BH3. If you look at the picture in the middle, you have the center atom, and then you have 3 bonds. This is called trigonal planar. You have to know the name as well as the structure. What do we mean by trigonal planar? Trigonal, trig means triangle. Planar means flat. So this translates to flat triangle, which is exactly what it is. That it describes the shape perfectly. It is a flat triangle. That looks like a Mercedes-Benz logo. Okay, it is a triangle because you only have 3 things. There's no lone pair to repel them. Okay, so what if one of them is a lone pair with only 2 bonds? That will be AX2E. Okay, they're in the same family as AX3 because they have 3 steric numbers. But the shape is not trigonal planar. The shape of the molecule would be bent because you cannot see electrons. The 2 lone pairs are not visible. You can only see the bonds between the atoms, so it looks bent to us. An example would be SO2. Remember we did the Lewis diagram for SO2 yesterday. Sulfur in the middle with 2 double bonds with 2 oxygens, and finally a lone pair on top, and the molecule eventually becomes bent. All right, and the last possibility for 3 steric number will be AXE2. You still have 3 things, it's just that now 2 of those things are lone pairs and only one of them is a bond. And this will be linear because the 2 lone pairs become invisible. You only see 2 atoms bonded to each other. Example will be oxygen. And again, it's similar to hydrogen. It is silly to consider one of those in the middle, but if you do, 1 oxygen in the middle, well, what's it bonded to? It's bonded to another oxygen. There's your X. And also that oxygen has 2 lone pairs. So that's your E2. All right, so that's AXE2. So those are all the combinations of steric number 3. You got any questions about that? No? Okay. I hope you see the pattern. Okay. If you have the same steric number, you draw this the same way. You have a middle atom and 3 things sticking out. It's just a matter of how many of those things are X's, how many of those things are E's. Okay. Now with 4s, you have 4 possibility. The tetrahedral is all X's, AX4. Okay, 4 things sticking out, all of them being bonds. Methane is that example. A tetrahedral is the name. Tetra means 4, hedral means shape. So a 4-sided shape. If you move on to the next row, you still have 4 things. So you still draw a tetrahedral, but you know that one of them is a lone pair. Only 3 of them are bonds. So ammonia is an example. So it has a different name. This is called trigonal pyramidal. Again, trigonal means triangle. Pyramidal, it is a pyramid. Okay, a triangular pyramid, which describes the shape perfectly. Okay, because you are unable to see those electrons, all you see is basically a tent or a pyramid like that. You see what I mean? So that's AX3E. The next 2, the next one is bent just like before. Okay, when you have steric number 3, you had a bent one. Well, you can have a bent molecule if you have a steric number of 4. AX2E2, the perfect example is water. You have 4 things on the middle atom, the oxygen. Okay, 2 of those are bonds and the other 2 are lone pairs. And you can't see those lone pairs, so you just see the bent molecule. So you can be bent in many different ways. You can be bent for different reasons. You can be bent because you had one lone pair. You can be bent for having two lone pairs. Okay, just because you're bent doesn't mean you have to be one particular thing. But notice the structure of water. It is still, if you count the electrons as well, it is still a tetrahedral. It's just that in that tetrahedral, you can't see two of the things coming out because they're electrons. So imagine my fingers as the two hydrogens. Well, the lone pairs are like this. Okay, imagine my hands stacking on top of each other. That will be water. You can rotate this, and they will point in different directions. So here is the reason why you must draw water as bent, because the three-dimensional structure of water is bent. If you draw them on a piece of paper as a straight line, you're going to get the wrong answer, and you're going to get the wrong properties. The last row is quite simple, linear, AXE3. If three of those four are just electrons, that means you can only see one thing, the bond, so it looks linear. All right, HCl would be the example. Chlorine has one bond with the hydrogen and three lone pairs, and you see none of those three lone pairs, so HCl is a linear molecule. So I hope this is clear. Any questions about steric number 4? All right, now it gets messed up. Steric number 5 is the hardest one to remember and visualize. If you have AX5, that means you have 5 things sticking out. All of them are bonds. Okay, so like phosphorus pentachloride, for example. First of the name is trigonal bipyramidal. Trigonal meaning triangle. Again, you can see that there is a triangle in the middle. One bond goes up, one bond goes down with a triangle in the middle. Okay, that's why it says trigonal. Bipyramidal. Bi means two. So there are 2 pyramids. It's like 2 pyramids stacked on top of each other. So double pyramid, bipyramidal. So that's trigonal bipyramidal. Okay, does that make sense? The next one, AX4E, is the hardest one to visualize, in my opinion, because in that trigonal bipyramidal, one of them is an electron pair with 4 bonds. Now, which one is the electron pair? It happens to be one of the corners of the triangle in the middle. So imagine the trigonal bipyramidal of the picture on top. You tip it over on its side, you will get that. And one of those triangles, that's the electron. So you still have 2 things. One goes to the left, one goes to the right. And a triangle in the middle is just that, that triangle has a lone pair. That means you don't see it. That looks like a seesaw. Okay, a seesaw is just, if you don't know what that is, you sit on it, and one person on that side, the other person on the other side, and you just go back and forth. That's a seesaw. That looks like a seesaw. And the name of this shape is literally seesaw. And that's the hardest one to visualize. And the only example that I know of is SF4. That's a really difficult structure to draw. The other possibility, well, you can see that as you go down the column, the number of electron pairs goes up by 1. So the next one would be AX3E2. You still have 5 things. Instead of having 1 lone pair, you now have 2. Now, which 2 becomes the lone pair? Again, same thing. You imagine the seesaw. Instead of having one of the corners of the triangle as a lone pair, you now have 2 of those corners as a lone pair. So what you have left is literally a T-shape. All right? So that's why this is called T-shaped. I hope you can see that. And finally, if you have AX2E3, that means you have 3 lone pairs. So all of your triangle, the entire triangle in the middle, are made of lone pairs. So you just have a linear structure. And XEF2 would be an example. Yesterday we did radon dichloride. That was another example. All right, so stare number 5 is kind of confusing. You might have to stare at this for a while to click in your head. So do we have any questions? No, really? We're good? All right, so the last page will be steric number 6. Okay, there's technically 7, but I know we're not doing 7. It's too complicated. So 6. If you have 6 things sticking out, and all of them are bonds, so AX6, that means you have an octahedral. Octa means 8. Hedral means shape. So 8-sided shape. All right, so to draw that, you draw one line going up, another one going down with a square in the middle. And if you just connect all the corners, you have an 8-sided shape. Okay, that's why it's called the octahedral. If you have one of them as a lone pair, so AX5E, instead of having octahedral, the bottom one, I like to use the bottom one, not the top one. The one on the bottom becomes electrons, so you don't see them anymore. So what you do see is a square base with a tip. So that is square pyramidal. It is a pyramid, just like the pyramids in Egypt. You have a square base and a tip. Square pyramidal, square because of square base. This is different from trigonal pyramidal because trigonal pyramidal has a triangle as the base. And lastly, if you have 2 lone pairs, AX4E2, the top and the bottom become lone pairs. All you see is the square. You don't see the top or the bottom anymore, so you're not a pyramid. You are square planar. Okay, this is similar to trigonal planar, except trigonal planar is for triangle. This one is for square. So I hope you guys see the pattern between all of these. You do need to know how to draw the Vesper structures, and I know this can be a lot of information to just learn all at once. When I first saw these, I was overwhelmed. I'm like, wow, how am I ever going to remember all of these? See, I didn't memorize all of them. I studied the pattern. I recognized the pattern. So from the pattern, I can deduce what all of them look like. So that's how you remember. Don't try to just memorize all of them just like that. So use the pattern, recognize the pattern, and then you will clearly see what the shape and structure should be. Okay, and the names are very intuitive. The name tells you about the structure, like square pyramidal, that describes the structure. It's a square-based pyramid. Okay, so do we have any questions before we actually go into drawing these?
So like on a test, would you give us like the shape and then we would have to draw that shape? Or will you give us like a chemical formula and we're going to just have to know what it is?
Okay, good question. Normally, I would just make you draw. I would just give you a Lewis diagram. Or let's say I'll give you, I don't know, ammonia. So draw the Vesper structure for ammonia. That would be your question. Problem is, you're doing your test on Google Form, and you're not able to draw on Google Form. So you won't be drawing anything. Instead, I'll find a different way of testing. For example, I'll give you 4 pictures in which of the following is square planar. You see what I mean? Something like that.
Okay.
It's
So we just have to
I can
recognize
do like AX5E and ask you what is the name of this shape. You see what I'm saying?
Okay.
Yeah. So yeah, there won't be any drawing, unfortunately. Well, you guys are probably sighing for relief here, but yeah, like unfortunately for me, you can't draw them. All right. Okay, so here we go into the examples. I will show you the first few, and then I'll assign the rest for you guys to just work on, and then I'll take up. All right, so first one, water. I'll draw the Vesper structure for water. So you got to first identify the Ax notation. Tell me the name of the molecular shape, and then finally with the Vesper structure. So in order to do that, you have to draw the Lewis diagram first, right? Because if you don't draw the Lewis diagram, you wouldn't know what the Ax notation is, and you don't know how many things are attached to the middle atom, you can't draw Vesper. So if you draw water out, H2O, you should realize that it is AX2E2. Okay, we already did water previously, so it is AX2E2. And that translates to a bent structure. Okay, so what would the Vesper structure be? Here's how I would draw that. I draw the oxygen in the middle. I draw the tetrahedral shape. Okay, one line going up with the same plane as the page, another line going sideways diagonally with the same plane as the page, so 2 solid lines. the third one coming out, and the last one going in. And then I will label them as either a hydrogen or 2 dots for the lone pair. It doesn't matter where you put the hydrogens or the lone pair. You can mix this up. It doesn't matter, because you can just take a water molecule, you rotate it in 3 dimensions, and you will get the other configuration. So they're literally the same thing. I happen to have chosen the lone pair to be on the 2 solid lines. There's no reason for that choice. I just wanted to choose that one. You can choose anything you like, okay? But you do have to draw that line. The reason is I want to see the direction of those electrons. Okay? It's not enough to just dot them. I want you to tell me that you know for a fact that the shape is a tetrahedral. Okay, so make sure you draw the lines now, even for lone pairs. Is that clear? All right, so that's water. The next one, PCl3, I'll do this one as well, and then I'll assign the rest of them. So for PCl3, the X notation, that would be AX3E. How do I know that? Simply draw the Lewis diagram, okay? And if you don't know what the Lewis diagram look like, let me just draw that real quick. You have a phosphorus, you have 3 chlorines, and a lone pair. Okay, I'm not going to bother drawing the electrons on the chlorines. That's a waste of time. So that is your Lewis structure, and we learned how to do that. So just if you need time to work on this, to draw the Lewis, please do, because you need the Lewis. So once you have that, it's really clear, AX3E. The shape would therefore be trigonal pyramidal, okay, like that. And to draw the Vesper, again, you draw the tetrahedral. Okay, you draw exactly the same as methane or water, a tetrahedral, 1 line in the same plane, 1 line going to the side in the same plane, 1 comes out, 1 goes in. It's just that when you attach the atoms, you just go with chlorines, 3 chlorines and 1 lone pair. I like to put the lone pair on top. That is the most aesthetic way of drawing this. So here you go, that's PCl3. Does that make sense, folks? All right, so I believe there are 8 examples. So please work on the next 6 examples. I'll take them up in around 10 to 15 minutes. It depends on how much time you need. So I'm going to pause the video and please start now. Okay, so let's start from example 3. So you have PCl5. The X notation is quite simple. It's just AX5. The phosphorus has 5 bonds, each with chlorine. Doesn't have any lone pairs. So the molecular shape will be trigonal bipyramidal. And if you want to draw the Vesper structure, you should have something like this. Phosphorus in the middle, 1 bond goes up, 1 bond goes down, 1 bond to the side, that makes a sideways T. And there should be a triangle in the middle. So in the middle, 1 chlorine comes out, 1 chlorine goes in. I hope you guys got this. So for the next one, example 4, yeah, this is a tricky one. You have to first of all draw XEF4 first. All right, and that can be pretty hard to draw. But once you draw the structure, you're going to realize that this is AX4E2. Okay, does anyone have a problem with that? No, you all got it? All right, so once you have this, the molecular shape is square planar. Okay, that's a hard one because it has 4 different bonds and 2 electrons, so the square is intact, but the up and down are become electrons. And the structure will look like this. Okay, so XC in the middle, you draw the square, that is the perpendicular square to the page. 2 comes out, 2 goes in, and you attach some F's on it. The thing that goes up and down, you have just 2 lone pairs, so that would be the Vesper structure. Number 5, this one is easy, SF6, that is just AX6. If you see something with 6 things on it, it's going to be octahedral. It doesn't have any lone pairs, so it's the same as before, as the XEF4, except this one, you don't have any lone pairs. You just fill everything with F's. And example 6 is tricky because you got the special one with the Lewis diagram. It makes no difference, okay? Just because this guy has a single lone electron, it doesn't mean you change anything about the X notation. That single electron still does the job. It will repel the molecule down. So it's still AX2E, and the shape is bent. And to draw that, well, you don't need to really draw a Vesper structure because this is technically correct. It is a flat molecule. Of course, you could draw it sideways. Let me just show you what the other possibility is. So you have drawn N, double bond oxygen. One of this can come out. That will be your oxygen. And another one could go in. You can do it like that. That is still the same thing, a bent molecule.
Wait, so we have to show double bonds?
Yes.
Okay.
Wait, you didn't?
No.
Oh, okay. Yeah, you have to show double bond.
Okay.
You might be thinking, wait, that's really inconvenient. If I have a double bond and they all come out of the page, do I have to draw two triangles? Well, technically, yes. So that's why I tried to not make that happen. Notice that I deliberately chose double bond to be in the same plane, so I don't have to do that. It's just a trick to make this easier to draw and prettier. Okay? You don't want to see two things coming out of the page as a double bond. That's confusing.
Yeah.
Wait, so do we have to show the valence electrons for oxygen too?
Oh, yes. Oh, wait. First of all, I see a mistake because there's one electron here. I put 2 dots. That's 1 dot. Do you have to show the valence electrons? Well, I really don't care because I'm testing you on the geometry, not how many valence electrons each atom has. That would be a Lewis diagram question. So honestly, I don't care if it's a Vesper structure. Sometimes I do it, sometimes not. It depends on my mood. So I wouldn't expect you to do it every time. But for Lewis, you have to have it.
So it's not wrong if we do Vesper without...
No. You can find structures of Vesper without any valence electrons because it's just convenient to draw it that way.
Okay.
All right, so number 7 is the tough one, HClO4. Okay, so first off, I want to start by saying that if you have a polyatomic ion with hydrogen attached, it's probably the acid version of that polyatomic ion. So this is perchloric acid. What would you do? Well, note that the hydrogen is not attached to the central atom. It is attached to the electronegative oxygen. Okay, so recall that if you draw ClO4 without the hydrogen, one of your oxygen will bear the negative formal charge. And that oxygen being more negative than it should be, it will try to seek something positive to bond with, and a hydrogen ion is the positive thing it bonds with. So ignore the hydrogen first. If you just draw ClO4, you will have AX4. The chlorine has 4 things attached to it with no lone pairs. So hence tetrahedral. So finally, the structure, that's what you would do. Chlorine in the middle, 3 oxygens, all double bonds, and 1 single bond. Now that oxygen will have the hydrogen on it, and that would be a perchloric acid. Now you might be thinking, wait, shouldn't one of those oxygens stick into the page, right? If you're thinking that, then you're right, it should be. Now why isn't it in the picture? Because the program I used to draw this with, it is unable to do that. It can do one thing coming out, one thing going in, but if I want to try to do a double bond, both going into the page, the program won't let me do it. So I can't actually draw that. But on paper, you would actually draw that. So it would look something like this. Okay, so those 2 should be going into the page. You see what I mean? Any questions? Okay, in addition, the hydrogen on the oxygen, okay, if you just take a look at this oxygen right here, that is another potential Vesper structure. That is a bent molecule. You see what I mean? That oxygen has 2 bonds, the chlorine and the hydrogen, and 2 lone pairs. Now your textbook will make you draw that as well. So you have a Vesper on a Vesper. but I think that's just too much work. That makes the drawing way too convoluted, so forget it. I'm happy if you just give me this. Okay, is that clear, folks?
Does it matter if I made the lone oxygen the one that goes forward instead of the
Doesn't
other?
matter which one you go forward, which one you go backward, because again, you can rotate this and you can get all the possibilities.
Okay.
Yeah, I deliberately choose the single bond to make it come out of the page because it's easy to do that with the single bond. You don't have to do it twice with the double bond. All right, so the last one, BRF3, a tricky one. It's really hard to draw the Lewis diagram of this thing, but if you follow all the rules like yesterday, you eventually should arrive at AX3E2. All right, and if you have AX3E2, you have T-shape, and that's one of the harder ones. Seesaw and T-shape, those are the really hard ones. And if you get this, well, here's what you do. You still try to draw this as if this is trigonal bipyramidal. All right, instead of putting F's on everything, you just have F's on the T-shaped part. And the two that comes out and goes in, you just dot them for electrons. And that would be BF3.
So it's okay if I put the ones that come out and go in on the top right? Like I can rotate that?
Oh, no, you can't.
It has to be that way?
Yeah, it has to be that way. You can rotate it, you can flip it like a mirror image, but you can't decide that the top and bottom are electrons because think about it, if you have that, that wouldn't be T-shaped, that would be a triangle. You form a triangle with your F's. You see what I mean? And that is not how it's found in nature. This is what you have. So you have to follow it like that. Okay, so that is not an option. All right, any other questions? All right then. If not, let me just show you this video and we'll be on our way. All right. Do we have any questions before we end this lesson? No, really? Okay. So yeah, that was Vesper structures. You guys need to know how to draw Vesper structures. And in order to do that, you need to draw Lewis structures. So make sure you really practice those. So I'm going to stop the video.